I hope you're off to have great Thanksgiving breaks. Since we're not in class today I'm going to catch you up on how to do an independent samples t-test, which is, in my opinion, one of the coolest t-tests. First, let's review when to use each t-test that we've learned so far. Sometimes it can be a little bit confusing to know which test to use. So I'm going to go through some examples to help you determine when you would use each of these types of t-test. A one-sample t-test is when you compare the mean in the sample to a chosen value, like 0 or a different value. Remember in class when I told you guys that we used this in a theft study I did? We wanted to see if giving people the drug Tylenol would cause them to steal more money from the lab. Now, why did we think this? Well, Tylenol can reduce not only physical pain, but emotional pain. We thought it might take away the emotional pain of guilt, and then people would want to steal more money from the lab. We made it really easy to steal from the lab. Participants were supposed to earn $12, but they reported to us how much they told us they earned. I wanted to find out, are people supposedly earning significantly more than $12? And they were. Now, Tylenol didn't affect it, but at least I could use that one sample t-test to determine, yes, people definitely were stealing from our lab. The dependent means t-test is also pretty interesting. You can use this to see if the difference score between two groups is significant. This is usually used to model change over time, or when people come into the lab twice and participate in both conditions. I used this test recently in a risk-taking study. My participants were going to undergo TDCS brain stimulation. I wanted to use a dependent measure to run my statistics because I had participants each get a real brain stimulation and then come in a second time and get a placebo brain stimulation. So the same person got both stimulations. For that reason, I had to use a dependent means t-test to look at my data. If I had had two different groups of people that didn't get both conditions but each just got one condition, I would use an independent samples t-test. This is the most common type of t-test because it's the most common experimental design. You can use it to see if two groups that don't depend on each other are significantly different. So back to the brain stimulation I was talking about. So I've made us up a data set of a study I want to run in the future. And as you guys know, in my research, I do brain stimulation by applying an electrode to a targeted area of the brain, making neurons in that part of the brain more or less likely to fire. So in this study I'd like to do in the future, I want to apply brain stimulation to a self-control region of the brain to see if it can help people eat less snacks. Okay? Now, research has shown that brain stimulation actually is pretty good at helping people not eat too much. And in my study, I need people to eat more than one or two things to have good gradation. So I think I'm going to tempt my participants with little cookies, little animal crackers. These are one of my favorite foods. So in this study, people will come into the lab and they'll get either a real or a fake brain stimulation, and then I'll see how many cookies they eat. So my data set that I made up looks like this. What you can see is the participant number on the far left, then in the middle a variable called brain stimulation, and it's full of zeros and ones. 1 means they got a real brain stimulation, and 0 means they just got the placebo. Finally, on the right, you see how many cookies they ate. Now, how do I do this t-test? Well, Let's watch. So let's break it down. We did the t-test, but how do we know what the results actually are? Well, you look at the sig column, okay? Sig is what we call the p-value. If sig is less than 0.05, we're going to reject the null hypothesis. There is a significant difference between the groups. To find out the nature of that difference, we would simply look at the means of each group and see which one is higher. Now, if sig is more than 0.05, we would fail to reject the null. The groups are not significantly different. So let's look back at ours. Let's see, I've circled some things that I think are important. The blue circle is just telling me what I'm testing. The yellow circle shows me the means for each group. The green circle is showing the t-value and the degrees of freedom. We'll go ahead and assume equal variances and use that top row for everything. Now the red circle is the most important circle here. It's circling the sig, or the p-value. It's 0.178. That's more than 0.05. So we're going to fail to reject. There's no significant difference between my two groups. The brain stimulation didn't make a significant difference in how many cookies people ate. Finally, the orange circle shows the mean difference, and the purple circle shows the standard error difference. There was not a significant difference between brain stimulation and the placebo on the numbers of cookies eaten. To write it up, you'll want to put it exactly like this, including the letters that I've italicized and what's capitalized and what's not. Don't get creative, just write it exactly like this. Now let's talk about effect size, or Cohen's d. For all intents and purposes, these are one and the same for you guys. It is the mean difference divided by the standard deviation. So let's compute it. We've got the mean difference and the standard error, but I don't see the standard deviation. So this is going to be a two-step process. First, let's get the standard deviation. The formula for the standard deviation is the standard error times the square root of n, or the number of people in the study. The standard deviation was 1.69. I saw that on the output. I'm going to times it by the square root of 10. I'm getting a value of 5.34. Now let's do the second step. Get the effect size, or Cohen's d. D is the mean difference divided by the standard deviation. So 2.5 divided by 5.34, and I got 0.47, which is a medium effect size. Remember, the conventions for effect sizes are 0.2 is small, 0.5 is medium, and 0.8 is big. Finally, let's do a power analysis. Now there's two types of power that we are discussing in this class: a priori and post hoc. A priori means before. This is the type of power analysis you would do before your study to see how many people you should test. if you want to have a certain level of power or a certain capability of detecting the effect that you're looking for. It's common for researchers to want to get 80% power or an 80% chance of detecting the effect they're looking for. We can also look at post hoc power, or the number of people you would have had to test to get the power that you needed, and the amount of power that you actually had in your study. Okay, so the post hoc essentially tells us, well, since you only tested this many people, your power was only this size. So let's look at how to compute it. Well, we only had 9 or 10% power there, so no wonder we didn't detect a significant effect. What I learned from that power analysis is that I would have had to test 146 people to have the 80% power that we want. So, with that in mind, this is how you do an independent samples t-test with some reminders about the differences between different kinds of t-tests. As you all are working on your projects, feel free to shoot me a message. Even over Thanksgiving, I'll be around doing some academic work. All right, guys, be safe and take care.